Alright, so what we're going to talk about next is Fermat's theorem. Fermat's theorem states that if f has a local minimum or a maximum, okay, it could be one or the other, at some number c, and if the derivative f prime exists at c, so f prime of c exists, then we can guarantee that the derivative must be equal to 0. Okay? So let's go ahead and draw a picture and illustrate what this theorem is saying. So there's some axes. Now this is just going to be a generic function, just something like that. And now let's say we're talking about right here. Let that be c. Now if I go up right there, that'd be f of c. Also, we have f prime of c. Now, we're going to illustrate that f prime of c must be equal to 0. Now, let's check the conditions for Fermat's theorem one more time. If f has a local maximum or minimum, right here, this is a local minimum because anywhere around c, f of c is always going to be smaller than any f of x anywhere near c. Okay? Now, we're going to also just let f prime of c just exist. Okay, we drew the function very smooth. There are no sharp points or corners. So now, if we were to look at it, think about what the derivative means. The derivative means slope. Right here, if I were to draw a tangent line, you would get a horizontal tangent right here at that minimum. Same thing goes for over here at a maximum. If I were to draw a horizontal or a tangent line at that point, it turns out to be a horizontal tangent. What is the slope of horizontal tangents? Well, horizontal lines don't have a slope at all. Their slope is 0. So if the derivative means slope, f prime of c at this number must be equal to 0. It must be equal to the slope of that tangent line at c. Okay? So now let's go ahead and go through the proof of this. Proof's not bad. It requires you to remember the limit definition of a derivative. Now, what we're going to suppose that f has a local, now I'm going to do the proof for a local maximum, okay? You can write up a very similar proof using doing the local minimum. So suppose that f has a local max at x is equal to c. Now what we're going to do, let's write the definition. What does it mean to have a local maximum at some value? Now if you look at the definition of a local maximum, a function f has a local maximum if f of c is greater than or equal to f of x when x is near c. Okay? Now, that's very important. When we say near C, we mean very, very close to C. So that when we're close to C, f of c is always bigger than any f of x. If you remember me talking about the definition of local min and max, you don't want to go too far out because then you can get more mins and maxes in that interval, but you want to be very close to this c value. So let me draw you a picture. Now, since we're talking about a maximum, I just drew a hill. It's not necessarily a parabola. So if I were to draw the axes, down here would be C. If I were to choose some x over here, right here would be f of c, you can easily see that f of x is definitely smaller than that f of c. Okay? And that would be true for any x that I pick. Now, let's say that the distance between c and x, let's call that distance h. If we call that distance h, we could rewrite x in terms of c and h. X would be equal to, well, I'm starting at c, and I'm going a distance h away, so I'm c plus h away. Now, what I'm going to do is I'm going to rewrite this piece right here to say f of c is greater than or equal to f of c plus h. And then I'm going to do one more thing. I'm going to subtract this f of c over to the other side. So minus f of c minus f of c. So we get 0 is greater than or equal to f of c plus h minus f of c. Oh, something I forgot. Since h, we're going this way to the right, we're assuming here that h is a positive number. Now that's going to become important because we got to do a second case when h is a negative number, and instead we're going to go somewhere over here. We're going to go that way, and this one would be c plus h, but since h is negative, we're actually going that direction, okay? Now this is going to be important because we're going to need to take a limit, and that's going to help us decide whether it's a right-handed limit or a left-handed limit. So I need this piece right here. So I'm going to erase everything and I'm going to rewrite it up top. Now as I'm erasing, think about what that looks like. You've seen something like this before. 0 is greater than or equal to f of c plus h minus f of c. Now that you've had a small time to think about it, think back to chapter 2. This looks like the numerator for the limit definition of a derivative. Okay? The only thing we're missing, oh yeah, h is greater than 0. I didn't mean to erase that. The only thing we're missing here is I have to divide both sides by h. So divide both sides by h. The fact that h is positive doesn't change how this inequality looks. Again, when we do the second case when h is negative, it's gonna do something, okay? Now 0 divided by h, 0 divided by anything is 0, is still greater than or equal to, I'm gonna leave a space right here because we're gonna write something, f of c plus h minus f of c all divided by h. So we really want a derivative. Right here is the limit definition of a derivative, but we're missing something. We're missing the limit. So what I'm going to do, I'm going to take the limit as h goes to 0 on both sides. Now, we have to take a special limit here. Remember, h was greater than 0. We were to the right of c. c was at top at our maximum. So if we want h to go to 0, that means h would have been shrinking and it's moving towards the right, or sorry, coming from the right. It's moving right to left, so it's coming from the right. If you remember when you're taking limits and you're coming from the right, you have to put a plus sign here because that is a right-handed limit. So then when we do the case when it's less than 0, you probably could realize that we're going to do a left-handed limit. Okay, so limit as h goes to 0 of 0. Well, this doesn't have any h's in it, so this limit doesn't affect this, so it's still going to be 0, is greater than or equal to. Now, here's where we're going to make our next assumption. We assume that, we said suppose that f has a local maximum at c. We're also going to suppose that f prime of c exists. If f prime of c exists, the right-handed limit of this difference quotient right here must also be equal to f prime of c, since we're assuming that the limit exists. Remember, we assume the two conditions are true, and then we're going to show that the derivative must be equal to 0. So this is one piece of our final result, okay? We're going to need this piece. So I'm going to erase everything. I'm going to write it up in that corner. 0 is greater than or equal to f prime of c. Now, we're going to assume that h is less than 0 in this case, okay? Now, I'm going to skip to this step right here. 0 is greater than or equal to f of, not x, c plus h minus f of c. What we're going to do is repeat the process, and we're going to get another result just like this one, and we're going to compare them, okay? So, if you recall, this looked like the limit definition of the derivative. The only thing that was missing was dividing by h. So that's what I'm going to do here. I'm going to divide both sides by h. Now, previously, h was positive. So, it didn't affect this inequality right here. Now, h is negative. I'm dividing both sides of an inequality by a negative number. You have to remember to flip the sign. So, this is still 0, is less than or equal to, I'm going to leave a space, f of c plus h minus f of c, all divided by h. Now I'm going to take the limit as h goes to 0, limit as h goes to 0, but now it's a left-handed limit because our h is negative. We're on the left side of c, so we're coming from the left when we get closer to c. Well, this side is still 0, which is less than or equal to, and then again we're going to use our assumption that f prime of c exists, so the left-handed limit of this exists, and it's equal to f prime of c. Okay, so this is the second piece that we need to get our final result. Our final result is to show that this f prime of c must be equal to 0. So we've got this one. Now we've got that one over there. Now, take a look at this one. It's an inequality. What you can do is interchange the sides of an inequality, and if you flip the sign along with it, the inequality remains true. That's what I'm going to do here. I'm just going to flip everything. So it's going to be f prime of c is less than or equal to 0. Let's read these for a second. This one says f prime of c is less than 0. I know it says equal to, but let's leave the equal to out for a second. F prime of c is less than 0. This one says 0 is less than f prime of c. Or in other words, if we read it the other way, f prime of c is greater than 0. How can some function value be less than 0, but also greater than 0 at the same time? It can't. Now remember, we have these equal to's. They could equal 0. So f prime of c does equal 0. Both of these things are true. And that is indeed the case. F prime of c must be equal to 0. You can even smash the f prime of c in between them and write one inequality. 0 is less than or equal to f prime of c, which is less than or equal to 0. Well, this has to be equal to 0 if it's between 0 and 0. So there's our final conclusion. That's the proof.